Okay, good afternoon and welcome everyone to this SMCB seminar series. As for those who have attended the last one, we have held a mini symposium on physical chemistry in medicinal research, and today we'll have another such special event, mini symposium on physical chemistry in material science. So this idea was floated by Professor Bagchi. That we should showcase that how basic fundamentals of physical chemistry can be connected to this somewhat applied research areas. So today we have two prolific speakers among us, Professor Anshu Pandey from IISc and Professor Rama from Delhi University. So I now request Professor Biman Bagchi to kindly start with his introductory remarks and initiate the proceedings.
Yeah, I'll be speaking only for a few minutes, but I do have prepared a which I want to share. Just a minute, where did that go?
There is a share screen button.
Yeah, I am trying to share. Now, you can see me now?
Yes.
Okay. So essentially, as Suman was saying, some of the appalling things happening, actually not in that much in US, or not probably in Europe, but in India, that I heard that few places the physical chemistry is getting kind of relegated. And I think one of the reasons that we probably, being the newcomer compared to organic and inorganic chemistry, we probably do not make enough noise, or actually the importance of physical chemistry. In general, many chemists do have a dislike of physical chemistry because of the math and the things. So, but we do have to probably make an effort to bring it, especially for the young generation, for the students, that it is how important and how fascinating this subject is. Of course, to us, this is the most fascinating aspect of chemistry. And so I just briefly summarize and put today's mini symposium in perspective. And so basically, as I said, the identity of the role of physical chemistry to emphasize that how important it is, and promoted through SMC and Sophic. And actually, one of the things that I have been thinking, that both physical chemistry of medicinal research and physical chemistry of in material science, they can be really nice chapters in an advanced physical chemistry, where the college professors and teachers can really tell that how important these things are, that how important some basic concepts. Okay, so I told you that it's just, I'll take probably less than 5 minutes, but just again for the students and even young faculty, a few things so that one can talk about. One is we have a huge number of topics, but a sub ensemble of that, these books. One is that, look, when we talk of synthesis, what are the things that really come in material synthesis? We need the concept of phase transition and phase equilibrium, the condition of supercooled or supersaturated state. We need nucleation, and that's very essential. Nucleation and the rapid solidification, where you, for example, in the semiconductor, you have to trap one material in the excess of the other, and the rate of crystal growth. All these things are done in physical chemistry. Crystal growth was done by Cohen and Turnbull, right? And Turnbull, particularly, Turnbull was in physical chemistry, and I think also in his department at Harvard. Then another very important thing we see all around is the spinel decomposition in all the ores and everything. Now, so this is the one thing that is, when you talk of synthesis, we should talk of nucleation. We should talk of crystal growth. These two are essential things, and they're, of course, dependent on phase transitions. Then we want to characterize the material we make. And that characterization requires all the spectroscopy, which is the first talk of today. the spectroscopy, IR, NMR, photoelectron, fluorescence, X-ray, electron microscopes, light scattering. Now, many of these things, the spectroscopy have been developed and applied and make the like NMR. One of the persons who does a lot of work is Ernst and say at Bagchi. They are all physical chemists. They got Nobel Prize in chemistry. And at Bagchi, at our time, we told he would get it. And they are in chemical physics department in NIH. Then light scattering experiments, level spectroscopy, they are all, this is why physics and chemistry overlaps. Okay. Then these things, we also talk of materials, and they are very much need of physical chemistry, like batteries and electrochemistry. The second talk, organic semiconductor, MEHBPV, someday we probably would have something on these beautiful subjects. And the singlet fission and all the things that going on, even in my department SSCU, some work is going on that. So there is always a beautiful thing between theory and experiment. One is scattering constriction, and that is we write down the electromagnetic expression. Then Fermi gold is Biman and Picora has done a wonderful job. So did Oxtoby in many of the reviews. Then we do the Fermi golden rule. Then we use Liouville propagator, and we go to the time correlation function presentation of, say, scattering cross section. What we measure in neutron scattering, which is an essential part of our understanding of liquids and solids and all materials. Is essentially this relation between theory and experiment, which is heavily, like Biman and Picora, for example, Oxtoby, heavily on and that whole formulation was done by Roy Gordon, 1966, in his Journal of Magnetic Resonance. So this is all our physical chemistry have done that. And then, of course, electric and thermal conductivity time correlation function formulation. I refer the students to beautiful citation, classics, and enormously influential 1/6 annual review of physical chemistry. That's why electrical conductivity lambda, then diffusion, they are all nothing but time correlation function. These are all very intimately related to our regular everyday study of physical chemistry. Two important expressions from physical chemistry we used in material science, and people don't mention these things. One is forced energy transfer rate in 1/R6. That was by Forster and Hoffman, Forster's, Then breaks down on short distances, which need to be known and noted. And then, of course, Marcus electron transfer. I refrained myself from going into any detail on Marcus electron transfer rate, but this is a famous parabola that this experiment showed, and that is used enormously. Like when I say my colleagues, so this Patirao says that talking of electron transfer everywhere, then it is essentially everybody is a Marcus electron transfer rate. I was not surprised. I had a book on these materials, physics, kind of physics, and there is just everything almost with Marcus electron transfer reaction I have studied. So computer simulation in material science, very important. This I want to point out. First MD was done by Holder and Wainwright, 1953, in series of paper. So sometimes we say MD 60, that's wrong. Anshu Rama came much later, 1964. He did continuous potential, but much of the results was that why Holder and Wainwright did not do. They did a hard, because all the results were known for hard. You see, from J.D. Barnard's experiment and all these things. Hard sphere was they wanted to find out. So they had these hard sphere phase transitions. A lot of work between 53 and 53 or rather late, but 54 to 63, 4. Continuous potential with Anshu Rahman, fast protein dynamics by Karplas and several people. Yashwanath and Rao from our department carried out fast quantical simulation of solids with the help of Anshu Rahman. Okay, and there are a lot of work, and these are picked out. You understand more or less pathway, but last two I talked of materials. Okay, the ones I know, and I didn't have to do much more. Okay, so who carried out their fast MD? Please look up this beautiful article by Holder and Pioneering Times of Molecular Simulation. There are all the references are there. Liquid materials, we have everyday work, binary and more complex mixtures. We have very, very important materials in binary state for all synthesis in industry. Then ionic liquids, there's a lot of things going on. Solid materials, glasses, liquid crystals, solid polymers, solid electrolytes. We'll talk here some of these things. then often not recognized or appreciated. Physical chemistry play important role in science, and that I think I'm doing essentially salesman job and trying to do salesman job to people who probably don't need to be sold, but still I think it is better to give a talk about it. And so I think with that I stop, Sumon, and I stop sharing. Thank you. Thank you very much. Sumanji.
Yeah, so maybe at this point you can introduce our next speaker, Anshu.
Yeah, good. Doing a good anchorman job. So today, first speaker is one of my favorite, Professor Anshu Pandey, who did the integrated masters from Bombay IIT. We know all about him. And then he did PhD in University of Chicago. He's an associate professor at the university, at the solid state and structure department at the Indian Institute of Science, and who has done huge amount of work. And is a prolific on many different areas, and is one of our best teachers in Indian Institute of Science. With this, I think I hand it over to Anshu.
Thank you to Professor Bagchi for the very, very kind introduction indeed. And thank you to the organizers for, Professor Sumit Chakravarti, Professor Ranjit Vishwas, Professor Rajiv Vishwas for organizing this wonderful meeting, and Professor Bagchi also for envisioning this sort of a thing. So, I'll try to do justice to the very kind introduction, but I don't know whether I can. So I'll today talk about time-resolved studies of quantum dot emission. More or less, this talk will be entirely focused on some ideas of growth of these semiconductors, but also about spontaneous emission rates in these materials. And, I'll try to show you why there are so many surprises yet to be found in something which is so elementary and simple. So,
just 1 second.
Yes, sir.
Maybe my sound box is problem. Is Anshu, Suman, is Anshu speaking sufficiently loudly?
Maybe I'll do one thing. I'll cut down some disturbance at my end and then try.
Okay.
Yeah.
Okay. Please go on. Sorry.
Yeah, I can hear you. No problem. Yeah.
Volume. That's why. As I'm growing old, I'm losing hearing power.
No, I hope I'm a little clearer now. I have tried to cut down background noise.
Yeah, it's much better. It's
much better. Wonderful, great. So yeah, Zoom must be cancelling out some background noise and cutting me out. So once again, thank you. So I'll try to conclude on time, and I'll be talking about two things. One is quantum dot growth, and a little bit I'll show how physical chemistry comes in there. And mostly I'll be talking about spontaneous emission rates in nanoparticles and why these are so very surprising, and we seem to be coming up with surprises even now. So yeah, what are quantum dots? Luckily, this is a good year to be talking about quantum dots, because quantum dots, at least for this year, need no introduction due to the Nobel to Bruce, Ekimov, and Bawendi. And the entire point over here with quantum dots, nonetheless, because this is supposed to be more for a general audience and specifically for students. So just a very quick show of these beautiful pictures, which everyone is already familiar with. Quantum dots can be made from the same material and show very different colors of emission. And the reason why this happens is quantum dots sort of inhabit this wonderful magical window between molecules and bulk materials, where for a molecule you have a HOMO and a LUMO, which is the highest occupied molecular orbital and the lowest unoccupied one. In a quantum dot, you have a density of state. You still have large number of levels, but they're still discretized. You can still count them. And this sits somewhere between this very, very discrete manifold of a molecule and somewhere between this very dense set of states, which one would get in a bulk solid. So they are solid. They are more dense than molecules, but have a lower density of state than a bulk. And this leads to interesting non-bulk-like properties. And this is the original reason for studying these materials. So what are they intuitively, and can we get a physical feel for them? These are essentially, mostly what I'll be talking about will be semiconductors inside of my cell. So it means that we have some material like cadmium selenide or some other materials. In fact, today I'll be talking mainly of the others, which we create a small round globule of, and we have this surrounded by these ligands. These are quote unquote high in quality. What I mean by that is that these can be very, very luminescent. So these seem like well-behaved materials. These are rather simple to process. And these can be very readily incorporated into devices such as photodetectors, displays, and so on. And while the original conjecture was these would be great for photovoltaics, these have been sort of overshadowed greatly by perovskites, but they still remain as prominent materials in photodetectors and emission. And also they are rapidly gaining importance with the emergence of photonic and quantum science as their own subjects, because it has been found that these can be very valuable building blocks for both. Now, a bit of a caveat here, this figure does not show only quantum dots. There are some quantum dots and some other objects as well. But the important thing which I wish to just convey over here is why quantum dots are so important is ultimately not just because you can make a round blob, but in fact you can do many different things with it. You can have layering, you can actually grow things to almost atomic level precision. And this ends up meaning that you're actually utilizing things like temperature, reaction times, reagent choices, trace additives, and all of these can actually alter both morphology, crystallographic structure, and let you make materials which are basically limited essentially only by our imagination. And these can be really, really complicated indeed. And that's indeed the wonderful thing why quantum dots remain exciting and will become more exciting in the future. So why does any of this happen? Well, here I'll refer to something which I'm not an expert in, but even though we use it all the time, but again, this is one of those understated things which runs as an undercurrent. This is something called the Ostwald step rule, and I'm citing only two papers here, one by Professor Bagchi, which is this one, and another one by Van Santen. Now, the idea over here of the Ostwald step rule is mainly that unstable polymorphs seem to arise first out of a melt before the eventual material arises. And this has prominent effects for how nucleation proceeds, which is excellently described in both of these works, and how wetting occurs. For a clever synthetic chemist, there's one more dimension to this, because you have all these other associated metastable phases. These would vanish in bulk. These would not actually be ever isolated correctly in bulk, but rather they do exist, and they are important. Now, what this means is because there are all these local minima, and the chemistry which we use is like this wonderful interface of being partly governed by thermodynamics, partly by kinetics, we can actually intercept these phases and use them to our benefit. And that is indeed what really is the secret of colloidal chemistry, why we can allow materials to grow in very weird shapes or very weird structures, simply by being clever when we are, which of these phases rather we are intercepting. Are we working out of the melt? Are we working out of the metastable phase, or are we directly trying transformations of some kind of a solid? Let me illustrate what I mean by that. This is one wonderful work from long back by Liu and Giossione, where they actually showed that, in synthesis of gold type nanoparticles, what you have is you can have two different kind of nuclei. Now, the only difference between these is that, okay, the initial starting reagents used to make the nuclei are different, but when these are plugged into the main reaction, so over here, nucleation and growth are two completely separated sort of events. But when you take these nuclei and then plug them into the main reaction, depending on which nucleus you use, you get a totally different outcome. And this is, over here, this is happening simply because whether the nucleus is single crystalline or polycrystalline. And so therefore, when it's isolated, entirely decides on what the reaction outcome is. This is one such example where you can have radical changes in morphology and structure simply given what the original nucleus and how it was prepared and at what state was it intercepted. In our own work very recently, something related but much stranger was observed, which was that not just can this happen with the main material that you're interested in, this can happen with the participating reagents. In this particular example, what we showed, or what we found rather, was that when we use certain classes of surfactants, it is found that under reaction conditions, they tend to have aggregates form. If we intercept this and do a reaction at the time of formation of this amorphous aggregate, we get one set of outcomes, not necessarily very desirable, but anyhow, we get a certain outcome. If we, however, move on and allow after some time to form this metastable surfactant or polymorph, we would get a totally different reaction outcome, which in this case was our desirable one. But if we slow down things further, we would actually obtain the stable surfactant polymorph, which now, of course, we didn't do this, but this would lead to an outcome 3. But nonetheless, we know that the stable surfactant polymorph was there because we could actually observe the thermal parameters of our metastable polymorph and actually find out that, okay, this was just lurking in the background. And if we waited long enough, we would even get that. So this is just an example of how in colloidal chemistry, depending on when the reactions are intercepted, one can get totally different outcomes, not just because of the main solid doing its thing, the solid of interest, but even the surfactants and all the participating reagents also having the same sort of dynamic happening to them. So bottom line is, this is what makes nanoparticles and colloidal chemistry so diverse and gives it so much power. But that said, while I'm showing these wonderful TM images, these are the last ones which I'll show, and I'll not talk about structure anymore. Rather, I'll actually go back to working with rather boring spherical quantum dots for the rest of my presentation. But of course, I'll promise you that they are not that boring also. I'll be talking mainly about 136 semiconductors. Now, to introduce these to a general audience, it's very, very simple. If you are taking a 136 semiconductor, it means you have firstly a monovalent metal ion. This is what the 1 stands for. This can be copper, silver, or gold. You take any trivalent cation from the periodic table, and this is very general. Anything which is in its trivalent state is fair game. So it could be the classical ones, aluminium, gallium, and indium, or it could be something which you pick off from the transition metals and manage making it in a trivalent state. And lastly, you pick a chalcogen. In our case, we'll only limit ourselves to sulfur, selenium, and tellurium. This leads to a large class of materials, or a large library of materials just by combinatorics. And what is funny is that most of these end up being good semiconductors. So why do I want to go to this peculiar family, and what exactly is the fun thing about it? I'll be talking about photoexciting quantum dots. Firstly, what does that mean? Well, if I take a very regular quantum dot, it means that I have a valence band and a conduction band. For the most part, or for the entire part actually of this presentation, I'll be talking about quantum dots in a state where I have one electron in its excited state. So the one electron in the conduction band over here, and there is a hole or a vacancy in the valence band. I'll not talk about anything else, and I'll show that this state itself is filled with too many surprises for us to tackle conveniently. The other important thing I wish to point out is that there are these wonderful state labels over here. For example, 1s3 half, 2s3 half, 1p5 half. These may be off-putting to people who have just wandered into the quantum dot field, but they are nothing bad. They are actually descriptors of angular momentum. But the good thing for this presentation, at least, is we'll be dropping them all together, because it seems, at least as we learned later, it appears that for 136 quantum dots, it's a bit tenuous to actually be using these. So I'll actually avoid using these labels altogether, and only talk. And since I'm only interested in a single configuration, I'll just be talking about this without giving it any label per se. This is the first excited state. What are 136 semiconductors? A very quick introduction to them, how they actually look, not just what they are chemically, but how they look can be seen over here. These have really broadened absorption spectra and very broadened emission spectra as well. They have very large Stokes shifts. They are so large in certain cases that we could do tricks like this, where we actually have a very transparent window-like object, and you flip on a switch and you can light this up, because this is coated with quantum dots, and these are so transparent you can actually read through them but not even see them properly. Sorry, is there a question or something?
No.
I can go on, right? Yeah.
I have just one question.
Oh, sure.
Why such a large Stokes shift?
In this case, okay, this is a little complicated case. What's happening here are two things. One, which I'll talk about, there are actually defects in the valence band. They're responsible for part of the Stokes shift. The other part in this material is coming because this is actually an engineered structure where the electron is sitting in one semiconductor, the hole in another, and that is responsible for one part of it. So there are exactly two reasons over here. One, because of defects, which I'll be talking about in great detail today, and other because of this systematic structure which we have built, where the electron and hole are residing in separate layers which have this property.
So you get of the 1000 centimeter inverse, more than 1000.
Okay, sorry, I'm not prepared for centimeter inverse. This is an electron volt. In nanometers. Yeah, I talk nanometers and electron volts. I sort of lose my thread in centimeter inverse. But
we are old.
EV, this is 1.5 EV is the maximum.
Yeah, that's a lot.
That's
that I can convert that much. That means 12,000 centimeter inverse.
Pretty much, and it means that entirely the visible spectrum we can have absorption in the ultraviolet.
Yeah, exactly. Yeah.
So yeah, wavelengths, this is close to 800 now. This is around 750.
Okay. Yeah. Okay.
So yeah, and then the techniques which I'll talk about three of them. And this is of course open to criticism. Why do you want to talk about three? Why do you need three? And I'll also show that all three become really relevant for this case. The first one is time correlated single photon counting. Just to give a very quick introduction to this, since this is again a student level presentation. So in this particular technique, what you have is a laser source. This is a pulse laser source. So from this, at t equal to 0, a pulse is sent towards a sample. And as soon as this laser fires, and this can do this because this is a very systematically pulsing light source, it sends an electrical pulse as well, which is received by a clock. So now this clock acts as a stopwatch. And the moment this pulse from the laser turns up, it actually is like pressing the start button on this clock and it starts counting the time. Meanwhile, a laser pulse has reached the sample has absorbed it, and eventually, whenever the sample decides, it decides to release a few photons, one of which is directed to this detector. As soon as this detector receives that photon, it sends a second pulse to this clock, which is a stop pulse. So this allows us to measure when the laser actually fired and when we actually received a photon from the sample. We repeat this process thousands or millions of times, depending on what we are doing, and we construct a histogram. What this tells us is actually the lifetime with which the sample is emitting. So this essentially gives us some sort of kinetic trace of what is happening to the dynamics of the sample. We have a different technique as well, which is transient absorption. This is slightly different because it uses path length differences between two pulses to actually measure time. Multiplying by the speed of light and all. And the other thing which it's doing is that the first pulse is a very strong pulse. This is incident upon the sample. And this causes the sample to, start having an electron hole pair inside it. The second pulse, which is this orange pulse, then arrives and a detector checks how much is the change in absorption of this pulse with and without this particular blue pulse being present. So what this essentially does is it's doing the same business as TCSPC is doing, say, in emission. This thing is doing in absorption. So what we are seeing is, again, if there are electrons dwelling in any state, we can actually check or find out that indeed those electrons are still there. The third technique which we'll invoke is luminescence upconversion, or UPL. This seems at first blush just like time correlated single photon counting. And there's one obvious difference and one very subtle difference, and I'll get to it, the subtle one, as we go along. How this technique works is that this actually again uses the idea of measuring path length difference between pulses to measure time. What's happening here is, okay, you have a powerful pulse hitting the sample. This causes the sample to get excited. Meanwhile, a second pulse, which is arriving at different points of time, is directed onto this nonlinear crystal. The sample's emission is also directed onto this crystal. And at a very precise point of time, when both the sample's emission and this particular pulse are arriving at the same time, the light from this crystal, the light is amplified and this new color is sent to the detector. So we are not measuring the emission directly, but rather we are measuring only the new color of light, which is being produced by the sum of this pulse and this pulse, and whatever the emission is, coming from the sample. So the result is, in principle, what this technique does is, because it's using path length differences to measure as opposed to electronics, this has a very, very improved precision, because this is now limited by how good our pulse widths and path length differences are. There's further one big difference between this and TCSPC, and I'll talk about that more as we go along, because it's a little more involved. It's harder to describe over here. So I'll talk about that more as we go along. So again, there's this criticism which might come up, that are these three techniques actually redundant and we don't need so many? Well, to set that one aside, first of all, let's see what happens with a very well-behaved semiconductor, in this case, cadmium selenide, cadmium sulfide. So this is among the best studied of quantum dots, and this sort of seems to say, well, indeed, maybe those techniques are redundant, because if we look at TCSPC of these quantum dots, we find that, okay, TCSPC has poor time resolution, it measures things in nanoseconds, and we get a nice clean exponential trace. If we look at luminescence upconversion, indeed it's measuring shorter times, but it's only measuring the early time dynamic here. So it's effectively a blow up of this part. And it does not say anything new, which I would like to learn. It rather says essentially the same thing is happening. So the two techniques actually confirm each other that, okay, the other technique does measure correctly, but very little else is happening beyond that. Now let's look at our favorite system on which we dwell upon most of today, which is copper indium sulfide, Cad sulfide. So, please ignore this presence of cadmium sulfide here. This is mainly being put to improve luminescence characteristics, nothing much beyond that. The main hero of the story is copper indium sulfide, because you've already seen from the last slide that in fact this addition of cadmium sulfide does nothing else. It just improves luminescence, makes data interpretation easy, signal collection easy, but little else more than that in our context. So what happens here? Well, the first thing which you see here is, okay, you get a TCS, when you do TCS-PC, you get a very nice clean exponential, which is great. This again seems like a very, very boring material, perhaps not something one might want to look at in great detail, especially because it's very similar exponential, which makes it in some sense more boring. Nothing interesting is happening. If we look at this material's transient absorption, we find something similar. What transient absorption says, well, at t equal to 0, I have my pump pulse, or the main powerful blue pulse, which I had earlier, arrive, and this kicks quite a few electrons into the conduction band. In fact, it's been tuned to kick around 1 or less than 1 electron into the conduction band, so per quantum dot. So in fact, what we get is that once this electron resides, the absorption of the state decreases. That's exactly what is being shown. And because of which we get this very nice flat line. And it's a really flat line, which means indeed after the pump pulse arrives, for this duration of 0 to 200 picoseconds, nothing much of interest is happening. The electron is just happily sitting in the conduction band and doing nothing. It's great. Now we look at UPL. We are yes, sir.
I have a silly question. Is there a simple way to understand the single exponential decay? Is there one decay channel that is standing out?
What this material is doing, given the quality of these dots, mostly it is just radiative decay. It's decaying very slowly. So on this graph, you don't seem to be seeing much of a slope. In this graph, there is this slope, and this graph is my secret graph, because this is what I talk about for the most of the talk.
Yeah, that's not radiative.
That is not at all,
Okay.
It's something interesting actually, because this immediately starts contradicting. So this is a very leading and nice question. So thank you for that, because we get an exponential decay here. We get a very nice exponential like decay over here. But over here, we see very, very ill-behaved character, because this is showing a fast decay and then a flat line. So this is firstly a big surprise, because other techniques would say nothing of this sort should be happening. Now, what is the standard way to understand it? The standard way, and this is, done time and time again, and this is the only go-to route which actually has been done over the years for which this technique has been used. So this is really surprising that this is not going to be the final interpretation, but this is how it's interpreted conventionally. The conventional interpretation, whenever you see this very rapid decay in UPL timing, would be, well, what is happening is, okay, first of all, what do we measure? We are seeing an 11.3 picosecond transient, which is really fast. So this is this very rapid initial decay. This actually counts for 64% of my total signal, and a slower but not slow enough decay which follows, which is having a 3.8 nanosecond lifetime, and that adds up to around 36% of the samples decay. So these are substantial. This fast decay especially is very, very substantial. Now, the standard way in which you would interpret whenever you see something at these early times decay so fast would be that, okay, all I'm seeing is non-radiative decay channels. So how do we model it? This is very standard. This is part of undergraduate learning, where you would actually use it. You would say that, okay, I have kinetics at play here. So I have a radiative kinetic. I have a denominator which is made up of radiative and non-radiative rates. And this ratio of these two rates, the sum of these two rates and this thing, is my luminescence quantity. Great. So if we actually use TCS-PC to get an estimate of KR, and then we divide by KR plus KNR, what we would find, because we would say that, okay, this 11.3 and 3.8 are essentially KNRs. KR is my 300 or such like time constant, which I saw earlier. If I take this ratio, then I would actually realize that my standard kinetic analysis would pull out a quantum yield close to 0.4%. That's really, really low. In fact, that is wrong, because the actual PL quantum yield of this sample, as measured very carefully, is around 60%, slightly in excess of that. And there are other samples we measured over the course of time with quantum yields even larger, approaching 90%. And yet this dynamic seems to stay and stand out. So what is the surprising thing happening over here? It clearly is not a non-radiative decay channel. If we look at transient absorption, we find that there is a bigger contradiction brewing. Because if we look at luminescence upconversion, it's trying to tell us, well, the emission from the sample decreases very sharply in the initial 10 nanoseconds and then seems to be sort of stabilizing. Okay, the transient absorption in fact says, okay, look, I'm nice and clean, and all electrons in this same time frame are sitting in exactly the same state. The states are not changing. So the sample is doing something which is actually over this time causing it to emit less, even though nothing got de-excited at all. So the electrons never moved, and yet the sample's emission lifetime changes. How could this even be possible? They are all sitting in seemingly the same state as far as PA is concerned. So this is really a surprising result. So for this, let's go back and answer the question which I brushed under the rug, which was that what UPL actually does and why this is such a different technique, even though it's ultimately just a luminescence measurement technique. What it actually does is that this is measuring number of photons which are arriving over the duration of the second pulse, which is a gate pulse. So this pulse now has a name. I'm going to call it a gate pulse. And whatever photons are being generated by the sample over the duration of this pulse, which means over this pulse width, are what are measured by UPL. Leaving all the technicalities aside, that's exactly what it's doing. So what is this determined by? We can just simply think of it as a proportionality problem. We know that it will depend on how much of the sample is excited. So this is P, the population of excited state emitters. What else will determine it? It will be determined to good measure by how long this gate duration is. This is TG. And it will be determined, of course, by the radiative rate because of the sample. This I'll prove by absurdity arguments. Because if we think that the radiative rate is infinite, or radiative lifetime, sorry, I don't mean rate, I mean lifetime. If the lifetime is infinitely long, then in that case, the sample will never really emit any photons. And this means that the signal would actually be zero. On the other hand, this is very short. And of the order of the gate pulse duration, I would get a very giant signal indeed. So the number of photons measured at any one point by this technique is actually dependent on spontaneous emission rate of the sample as well, which makes it very distinct from both what PA and TCS-PC are trying to do. And now that we are actually seeing all this creates some interesting things for us, because this seems to suggest, because P is not really changing, that's courtesy of the quantum yield, that's courtesy of what TA is saying, P is not changing at all. This means that the radiative rate itself must be changing. Certainly, we are not changing the gate duration. So this establishes nothing else but that the spontaneous emission rate itself must be changing, which is a gigantic surprise to anyone who knows what we are talking about over here, because we also were very surprised seeing this. So let us do one more thing with this proportionality. We can actually take two separate materials. We can take cadmium selenide, which is well understood, done to that. Again, I'm talking about its sulfide variant, where we have coated it to make it more understandable and easy to understand. And we can take this thing as a ratio, because over here what happens is we end up cancelling whatever undesirables are there. And what we find out as a consequence is that when we are taking cadmium selenide and referencing it, we can actually take the cross sections, which are very well known. And then what we find out in this lifetime is also very well known for cadmium selenide. This is around 27.2 nanoseconds for the sort of samples which we are studying. This allows us to directly estimate, based on the signal which we are getting, the lifetime which is there for copper indium sulfide, Cat sulfide. Please note of one thing, that this lifetime can only be measured or accurately at t equal to 0 picosecond. It's not a very valid procedure anywhere else. It's only valid at t equal to 0. And this says that this lifetime, based on the luminosity of the sample at that instant, is 46 nanoseconds. That sounds very interesting. Great. I've taken a ratio and I have a spontaneous emission lifetime for copper indium sulfide. Wonderful. Sorry. Yes. Okay, so now, however, let's just compare with what we have already seen, and we realize we are getting into even more trouble. Because if my spontaneous emission lifetime is actually 46 nanoseconds, let's note about one thing. My emission lifetime as measured by TC-SPC is far, far, far longer. This is 300 nanoseconds. So this shows what a ridiculous situation we are in. I'm seeing a spontaneous lifetime at t equal to 0 in the UPL, which is very short, but the emission lifetime, which TC-SPC seems to be leading to, is very, very long. But luckily over here, a good thing happened, which is that we sort of kind of already know which answer we are getting, because in UPL itself, we find that the trace is sort of flattening out, it's lengthening and decreasing in its amplitude. What this means is that the UPL trace is actually showing some sort of a variation in the lifetime. And in fact, why it's heading downwards is my spontaneous lifetime, which starts off very, very high, is actually lengthening to the value which eventually TC-SPC observes. TC-SPC is very blind to whatever is happening initially. It's also not a technique sensitive to these variations in spontaneous lifetime, not in the way that UPL is. And because of which, this has never been noted, even though people have seen very, very flat dynamic, which seems, completely boring.
Anshu, one more question, sorry. But these kind of situation, one does not really experience the 46 nanosecond to 294 nanosecond in bulk materials, right?
Absolutely. No, bulk, I don't know. There are no studies of this in bulk phase, unfortunately for me. So it would be fun to study. My belief is it will occur even in bulk. But this is peculiar to this family of nanoparticles. Peculiar to this, family of semiconductors, not of nanoparticles. Again, caveat is bulk, no one has reported studies of this sort.
So it will be connected to some kind of electron dynamics?
Absolutely. I'm going to make that connection. Absolutely, yes. I'll try to show that connection now. But it is likely to persist in bulk, even though I don't know that for sure. So, to sort of make the long story short of what we eventually did, we actually used this procedure of deconvolution. Deconvolution can be very dicey if we, make a mistake. So what we decided to do was use 3 separate models. We tried to vet whatever we were doing on CDSE, CDS. We find that, okay, this is as advertised, a very boring material indeed. Nothing of interest happens here at all. Its spontaneous lifetime is flat within the experimental noise. But if we look at copper indium sulfide, Cad sulfide, its spontaneous lifetime changes. As already advertised, it is changing from 46 nanoseconds to roughly 294 nanoseconds. So why exactly this is happening? And as Professor Bagchi already anticipated, there is some kind of an electron transfer going on. Very specifically this, there is a very subtle change in energetics also, which is important, but it's so subtle and so instantaneous, one might miss it if we don't look at the spontaneous lifetimes very carefully. And the entire point over here, what is happening is that the valence band holes in this material, which PA is very blind to, are initially in a very delocalized state. It appears at least to be like that. But as time elapses, more likely around 10 picoseconds, which is where we see all these changes to be complete, in more or less all of the quantum dots, this hole has migrated to a localized state. Now, this is a direct observation of this sort of dynamic and what is happening as a consequence, because now this state represents a totally new kind of transition dipole. We are seeing this smooth change in the entire sample from a radiative lifetime of 46 nanoseconds all the way going to 294 nanoseconds. Even though it's happening in the same material, other properties are remaining roughly unchanged. We are not seeing major changes in the material's emission, except that its lifetime, everything else is almost imperceptible, but its lifetime seems to be changing drastically. And that is the really, really weird observation over here. So again, why is that happening? We can study this in detail, but I will not make this, discuss this today in order to keep things simple. The point is we did actually try to understand this in more detail using electron transfer theory, and this actually helps us a lot. What we found was that if we use simple models of electron transfer together with Huang's radiative decay, what we are able to do is entirely model all the spectroscopic properties, all key spectroscopic properties of these quantum dots using just these 2 models. And then we also figured out some stuff about selection rules and how they are applicable or not applicable rather to these materials and why they fail in the system. But I'm not talking about this aspect of detailed quantitative calculations based on these models today, but rather I'll move on and try to take a slightly simpler and easier route in the last 10 minutes or so that I have about what the intuition behind all of this is. So even though this is intuitive and literally a hypothesis, it is a hypothesis. Still, it would seem that this localization or whatever interplay these holes are doing might be linked to copper. And the reason why it might be linked to copper is that copper is an infamous yarn tiller ion in its D9 configuration, but not in its D10 configuration. So when we start off, copper is always in the D10, but it's likely that when the hole sort of collapses, it's probably doing it on a copper which has gone D9. And this might be the entire reason why this material is doing whatever it's doing. It's of course a hypothesis, completely unproven, but can this hypothesis actually help us make copper do other interesting things? And that's an open question. So we did try to answer it. And certainly when we say interesting things and our talk is mainly about spontaneous lifetime, we will talk only about that. So what we decided to do was actually look at copper, not just in the dilute limit, which is rather well studied, but actually move on towards the concentrated limit. And what happens over there is we are putting so many copper atoms. So what is studied most often is when you add copper into, say, a well-behaved 2,6 material like cadmium selenide, it introduces a state over here, which is an atom-like state, and conduction band electron can transition into that state. So this state, its existence, etc., are very, very well studied. But what is studied about them is in the dilute limit, where we have around 1 or 2 copper atoms inside. What we wanted to look at was the concentrated limit, where we have more than 1, which may go to 2, 3, not 2, 3, but rather tens of copper atoms. So much so that they start having an interaction. This is what is sort of shown here. So first of all, what happens? This sort of a picture is immediately connected again with undergraduate level physical chemistry courses, because we are looking at some sort of an MO diagram over here. What is happening in fact over here is that the states which are forming at lower energies would always have a symmetric overlap. They would be more symmetric, while the states at higher energies would be less symmetric. And the immediate consequences, spectroscopically speaking, all of the oscillator strength is mostly borne by these more symmetric states at the bottom. So overall, when you start adding copper, you become blind to these higher energy states. And at the same time, what appears to happen is that the entire luminescence band, as the amount of copper increases in the system, seems to blue shift, gravitates towards the band edge of the material. So it's not to say that the entire copper, all of the copper atoms are increasing in energy higher up. It's not like that, but rather they are actually being pushed down towards the valence band. And this state is responsible for the entire effect, because it is carrying all the oscillator strength, and we go blind to these higher energy states. So there are other consequences. There are some unusual things which copper does, which we understood only in part. It seems to radically change the spectroscopy of the material right around 15% loading levels, which we don't understand at all, because it does not seem to be related to anything physical that should be happening. But what is interesting is none of this change in its spectroscopy of absorption seem to interfere at all with the emission. So, emission is not being changed at all. And emission is still happening mainly from states which seem to be rather localized relative to each other. Now, why copper? And what is so exciting about copper? Well, what we found out was as we start increasing the amount of copper in the material, the emission from the material gets faster and faster. Now, this is what I would call a change in the rate of spontaneous emission. This is not yet showing spontaneous emission rate change. This is actually showing just faster kinetic. And before I can conclude that spontaneous rates are changing, I have to actually look at things like quantum yield. I have to look at actually measuring the luminosity of these samples using, again, UPL-like techniques to confirm that it is actually a spontaneous lifetime changing, not everything else. So we did all that. And I'll come to that in just a moment, but all these graphs are showing is that the lifetime is getting shorter. And we have to rule out non-radiative decay over here. And again, one important thing I'd like to bring in about this graph is the change in spontaneous decay is well known again in physical chemistry and outside, because this is generally connected with the Purcell effect, where you are changing the, connecting, say, a quantum dot or a molecule to a localized photonic density of states. You are changing its coupling to light. In this case, that is not being done. In this case, the material itself is doing something to itself, which is changing its rate of emission, which is, again, an unheard of idea, only happening in this sort of material. So what exactly happened, and can I confirm that this is spontaneous lifetime? The answer is yes. We did it via two means. We can look at the absolute quantum yields, we find that once normalized to absolute quantum yields, in fact, as copper increases, we find a very clear-cut decrease in the spontaneous emission lifetime, so much so that we are able to tune it over 3 decades, which is a lot. The second thing is we can again re-verify that as the copper amount increases, the sample is indeed getting faster in its emission by again using the same old trick which I mentioned earlier, which is to check whether it's getting brighter and brighter in UPL. The answer is it does get much brighter in UPL. And this tells us that the spontaneous lifetime is in fact shortening significantly. So long story short, what really is copper doing? Well, something like this. Each of these copper atoms in fact presents a new path. So the electron which sits in the conduction band wants desperately to fall back into the valence band. And it can do this normally just like this. But what each of the coppers does is that it gives it an alternate path through which to fall through. And because of that, the net rate which we measure is in fact a sum of all these rates. This leads to a very fast emission lifetime, which is again unprecedented. It's a very simple trick, a very simple idea of kinetics being played out where, we are not seeing any interference or anything else between paths, but rather just a straightforward sum, which is leading to these observations. So I'll stop here and conclude. We basically described a very unusual new observation of spontaneous lifetime, which is sort of sacrosanct for any emitter most of the time, itself evolving as a function of time, which is really an unheard of thing. It's like somebody's fingerprint changing as a function of time. This motivated us to look around a little bit more, sniff around copper a little bit more, and this led us to a new method to control spontaneous emission lifetimes, where we were not using the Purcell effect, which is the standard way everyone does it, but this affords a new way in which materials can be controlled by one more path. I'll thank all the people who did all the work. Everything I talked about today was done by Arpita Mukherjee, Vishwajit Bhattacharya, Preetha Mandal, Naveshri Vasudeva, and Parna Roy. So I thank all of them. I thank my collaborators only for the works which I've shown here, which are Professor Sheetal Jain, Professor Guru Rao, and Professor Mukesh Narayan. I'll over here, since again this is a tutorial type lecture, these are the main publications which I cited today, the ones by Professor Bagchi, Van Santen, Liu and Giosione, and also these are the main papers from our own work which I referred to today. So thank you for your attention, and I'll be happy to answer any questions.
Okay, thanks Anshu for a really nice and lucid representation of really exciting results. So there are some questions in the chat box, so maybe I'll read through them. And meanwhile, if there are some other questions, please feel free to raise your hand, and then we will go one after another. So I'll go through the chat box. First question is from Vishnu. Is there a thermodynamic parameter apart from the low activation barrier for nucleation in the case of unstable polymorphs being formed first and then later evolving towards a stable polymorph?
So this is more a question which I guess the organizers and Professor Bagchi are well versed in rather than myself, but I'll try my best to answer. So the question, let me just go over it one more thing. So
open the chat box.
Yeah, I see it. Is apart from the low activation barrier for nucleation in that case. So okay, so I'm being formed first and later. No, so this is actually slightly different. I think maybe the point is slightly different over here. What the Ostwald step rule says is that you are stepping through these polymorphs before the ultimate stable polymorph is actually resulted. And the interesting thing is, the point being discussed here is nucleation theory. And the entire point of these studies are that nucleation theory, classical nucleation theory, actually is failing completely because the presence of these polymorphs lowers the activation barriers ultimately because it improves wetting characteristics. And this eventually lets you find or seek the stable polymorph. So the entire idea, which however we are playing with, we are not treating the nucleation of the, in colloids, we are not treating the nucleation of the final stable polymorph as our ultimate goal. We are actually wanting rather to stop the reaction at specific points in one of these local minima, stop or slow it down, and then use it to do something else. That's essentially the entire trick of this chemistry.
Hey, Anshu, I must tell you one thing.
Sir.
Your understanding is almost perfect. Very nice.
Thank you. I read your papers very carefully.
That is, you have done a better job than me. Okay, go ahead.
Next question is from Ravi Kishore. Why transient absorption signal is not decaying?
So yeah, so great question. So this is again related to this flattening of this curve, which I had shown earlier on. Somewhere over here, this is related to this question of why is this like so much like a step function, say over here. So the answer is it is decaying, but if you notice the decay time will actually in this material be, for you to notice anything, you'll have to go to hundreds of nanoseconds to actually notice that it is sloping strongly down. Because we are only at 200 picoseconds. This is like the first initial step for this material. Its emission time or the dwell time of these electrons is really long. You would notice that this has decayed to half around 300 nanoseconds later. So clearly we are, roughly 1 order of magnitude too short in lifetime. In these techniques like transient absorption, UPL, because we are using path length differences, it is very hard to measure anything longer than a nanosecond. It's very unreliable. So we don't do that generally. We restrict ourselves to the first 200 picoseconds. And over there, this material is really quiet. It does nothing.
Yeah, actually, there is a series of questions from Ravi Kishore. So if you are here and you want to ask it yourself, please feel free to start. Yeah. Otherwise,
Thank you so much. And yeah, also nice presentation. So just wanted to check. So did you measure the so you told that the lifetime is changing, right?
Right.
And what about the quantum fields?
This is this set of results that you're talking about. This one.
Yeah.
This graph. Yeah. Right.
See, if your lifetime decreases, the intensity obviously will grow if you average it over you have to cycle between ground state and acceleration many times.
Mm-hmm.
The molecule, this one will cycle many times, right? It's a shorter lifetime. Say for
that is all taken care of. The way the measurement is being done. Yes, in a steady state measurement, you might worry about that. Are you cycling many times? But then the input light fluences are so low in steady state measurements that it's not a question which we worry about. In these measurements, because everything is timed with a laser pulse, and we wait for complete de-excitation before the next pulse comes, so that also does not become a significant worry. So they are not worries as far as these experiments are concerned, but yes, there is a separate point which you raised, which is very important, which is that would you like to use these materials, say, as biomarkers or in a biological application? Absolutely, yes. These will be better because these are much shorter time emitters than regular quantum dots. So there is a use which they'll have because they are doing it without a Purcell effect.
And you're doping with copper, right? Copper, this is what D9 you're saying.
Copper is, copper 2 would be D9.
D9.
So we believe that it is D9 configuration which is entering here.
But D9 is paramagnetic, right?
D9 is a paramagnetic configuration of copper, but there are many catches and caveats here. Which, since you asked the word paramagnetic, I must bring those up.
Yeah.
Which is, if you actually measure EPR of these quantum dots, they have no EPR signal. That itself has been a topic of several arguments. So they answer like paramagnetic species to ODMR, but in EPR they are very silent. And the reason for that, at least given long back, is that these materials are Yarn-Teller coupled, because of which EPR is essentially quenched. Because of spin orbit coupling, Yarn-Teller distortions, EPR gets completely quenched. You can see the D9 state only in ODMR, and you see it also because these materials are in fact photomagnetic. They actually show strong DMS-like character.
Generally, if a species is paramagnetic, they don't show fluorescence. I don't know about this nano.
They show. In the copper case, they are very fluorescent. Yes. So copper itself, okay, I understand. It's coming from an inorganic chemistry viewpoint. Yes, copper itself is not fluorescent. The precise thing which is happening is perhaps best shown in this diagram. The conduction band electron falls into copper as the first step, turning it from D9 presumably to D10, and then it relaxes thermally back to the ground state. But this initial fall is what is giving rise to the luminescence.
And why is there a blue shift?
Why is there the blue shift? Okay, again.
If you see it, your band gap seems to be decreasing, right? Your band, you told the band edge is shifting.
Right. So again, it's blue shifting because if you notice this particular graph here, or this schematic here. So firstly, this is the graph of blue shift. It's blue shift relative to the main host emission band. And the reason why this is happening is the copper energies are not changing. They are simply splitting, but all the oscillator strength is carried by the lower state. The outcome of that is, if you notice, initially I had to go this much energy, this was my emission energy, but now it will be this much. So this is higher energy, right? So this is why there is a systematic blue shift. This is approaching the host valence band.
Yeah,
that
I
is
think,
only when you have more copper, is it? So this is like,
Rovi,
yes, sir, yes, sir,
I
yes,
think you probably now can write to him,
yes, sir.
to Anshu, and because we have to go ahead. Huh?
Sure.
But I just want to, before I end, I just want very general question, Anshu. When you talk of these things about what do Einstein's theory of spontaneous emission, and you have two different ways of spontaneous. So how do you think of then Einstein's theory? Is there any change?
I think I will not touch Einstein's theory. I think no change there because he derived it considering that as a fingerprint single parameter. Now over there, what is happening here is you could still use the same theory because the initial brightness is just very high. But what is quite clear is at every point of time, we are associated with a spontaneous rate. So I believe that finally that is a theory giving rise to thermodynamics, that thermodynamics will still play out as making things thermodynamically consistent. So that will still hold.
I once tried to do this theory of spontaneous emission, and in our little bit of that has been done in our book in molecular electron liquid. But Anshu, I found it is terribly difficult to understand you need electrodynamics.
Yeah.
In a huge way. And all gauge invariants, gauge transformations.
Indeed. Now, this very detailed understanding and understanding these effects, how they are playing out in these materials, will be immensely complicated. That I completely agree. Because if this is changing, then it makes these materials harder to understand.
That was I was thinking that that's what I meant by some electron dynamics is a wonderful problem for theoreticians like Odes Narayan if I can make him do dynamics.
So definitely, I got some help from him. So.
Okay. I'm done.
Thank you. Thanks, sir.
Sure, thank you.
Yeah,
come on.
Yeah. So I think then let us all thank once again Anshu for an excellent talk. Yeah, and if you have any further questions or comments for him, please feel free to write to him. I'm sure he'll be happy to reply to you. Now, yeah, so now let's move on to our next lecture by Professor Ramakant. Now I request my co-organizer, Professor Ranjit Bishwas from SN Bose National Center for Basic Sciences to please introduce the next speaker. Ranjita, please.
Thank you, Shuman. As Shuman already pointed out that we are going to have another exciting speaker, Ramakant, who is theoretical electrochemist by training, but who does experiments by himself in his group. This is unique because he gets an opportunity to develop his mathematical equations for understanding non-trivial electrochemical reactions and then validate his equations by carrying out experiments himself. His work, particularly those mathematical works or theoretical works, dealt with electrochemical reactions at the disordered electrodes or structured electrodes are extremely important because they lead to critical understanding of many electrochemical reactions that are relevant to technological development of interesting materials. Ramakant received his PhD degree in 1993 from IISc Bangalore and got Professor P.G. Dijans as one of his postdoctoral supervisor during his postdoctoral stint in Paris. 2003, Ramakant came back to India and joined Delhi University. And since then, he's there and now a senior professor. And so far, Professor Ramakant has trained many PhD students, project students, and summer trainees. And he has become selected fellows of Indian National Science Academy and Academy of Science, Bangalore. With this, I request Professor Ramakant for his lecture. Ramakant, please.
Thank you, Professor Ranjit, for kind introduction. And I also thank Professor Bagchi for giving me opportunity to talk to you. And he cautioned me there will be a lot of students, including biology backgrounds, or like that. So some part of the talk, as Ranjit emphasized, that sometimes I used little more mathematics, but I will avoid all mathematics. And to simplify, we did some calculation, keeping audience in mind, explaining energy density in lithium-ion battery. That will be part of this initial part. And then we'll have electron transfer theory, and particularly how to remove the limitation of Marcus type of approaches to address more complex electrochemical electron transfer system. And then we'll follow it with some other calculations on when we have even irregularities like atomic steps, and some experimental work asking question to how to determine roughness through electrochemical experiment, etc. of an electrode. So with this, okay, we think first thing, okay, when a lot of people are these days working on applied aspect of electrochemistry, which include working on supercapacitor, large number of batteries, electrochemical devices, sensors, generating fuels from making hydrogen or converting carbon dioxide into useful organic chemicals. So there are plenty of them, and all of them have very complex electrode structure, because they are not simple one metal or so, many things are deposited over it. And so both cathode has its own complexity, anode has its own complexity. To optimize functioning of the electrochemical cell, it is done. So how to address all these things from fundamental angle and without resorting to extensive computation methods or while keeping very close to experimental facts also. So here we'll kind of think of, if you think of electrochemistry, there are two ways to look at it. One is material aspect, one is phenomena based. When we construct any device or we think about materials, that's what large number of people are trying to do. In materials, there are three components. One is electrolyte. So people try to play with electrolyte mixture of ions, and many ions are there, both in nature as well as people have synthesized also. Similarly, there are larger number of attempts are made to tune the electrode property, and people do both extensive experimental work in this area, as well as a lot of people do DFT and those kind of calculation to optimize this material property. And there are electroactive molecules, which can come from simple molecule of chemistry, ionic system, to non-ionic system, to large biological molecules. So it can be anything. So there are options in terms of materials are large, which can make electrochemistry as a very rich subject. But in practice, what happened, when we see the functioning of a device or even a fundamental electrochemistry, we are dealing with various phenomena there: electron transfer, charge accumulation, mass transport, and all those things. And all these phenomena has their own characteristic spatial length scale, temporal length scale, and energy length scale. So electrochemistry, one way one can say, is game of energy, space, and time. Of course, almost sciences are game of energy, space, and time. So same way, electrochemistry is also. So how to understand various electrochemical complexity based on this conceptual approach. So simple thing like when we think of electrochemistry, people have studied in their BSc, MSc about Debye-Huckel theory or so, where we have one, because of interaction of ions, you get a kind of effective screening length, because it's a many-body problem. And on midfield level, it mimics itself through one screening length, which is called Debye screening length. which is inversely related to ionic strength of the solution, and it's directly proportionate to dielectric of the medium and thermal energy of the medium. And the one common property which one see of electrolyte, diffusivity of various ions and conductivity of this, particularly the molar conductivity or so. So here where there is a famous law, students have studied like Kohlrausch law or so, where you simply add their conductivity of individual ion to get it. But that is applicable for extremely dilute solution, which is of very little practical relevance. Then came the modification of Onsager limiting law, which accounted, and then further modification, it allows to operate concentration, say up to 0.1 molar or even up to 1 molar, you can extend. We have seen some data and graph there. But when you are dealing with very concentrated electrolyte, which is the case of most electrochemical devices, whether you are dealing with a battery or a supercapacitor, you are dealing with very concentrated electrolyte. In that regime, there is no scope to extend this theory because of their nature. One reason is that because when we have screening length with concentration, screening length keep decreasing. It becomes smaller than the ionic distance or ionic sizes. So it is obviously that Debye screening length concept breaks down when we come to concentrated electrolyte. So we modified this Debye screening length on the, I can activate my screen pointer. Like here, you can see this. So here we have screening length, which is having in itself, or it's a function of Debye length, but it also has mean size of ion, both cation and RH represent that mean size, and goes, it says like a Debye length expand when you are dealing with a concentrated electrolyte. One region one can think of, it is entropic region because this derivation is done using that argument. Or one can think when your concentration is high, both cation and make pairs, so they are no more like ions. So it effectively suppresses the ionic concentration of your solution. Hence, your screening length start increasing when beyond the sizes, beyond the concentration where the device screening length become equal to the ion size. So this captures it. So it's a kind of non-monotonic function, device screening length. And then we kind of visualize like this ionic cloud around a central ion itself act like some kind of sphere, which is soft sphere. So if you see the molar conductivity equation on the right-hand side here, which has size of cation scaled with respect to our modified screening length and raised to power gamma. So gamma is a kind of factor which is like a hardness or softness parameter or something. When gamma is 1, whole ionic sphere, like the ion along with its ionic cloud, acting like a hard sphere. But that's not the real practical thing. So gamma is always less than 1 to mimic the softness of this sphere. So effectively in concentrated system, ion behave as though it is much larger than its original size. And in that case, you can do the weighted average of their ionic conductivity. So it's kind of modification. Yeah.
Rama,
yeah.
This is a wonderful slide, and you are doing really a wonderful job in explaining things. One thing I have that studies don't have, I know you are doing essentially long time so-called quote-unquote equilibrium things, but if you bring frequency dependence here, then you probably would be able to add one more
Yes. Yes.
and you can ask some more answer some more questions, no?
Okay, I will explain that, why I have not done that. Uh, in electrochemistry, when we have electrode, electric double layer charge transfer, the frequency of particularly where you see the ohmic part of the cell, that is very high frequency. That comes around megahertz or sometimes 10 to 5 hertz or kind of thing. So this is the, like in typical electrochemical measurement, this is the upper highest limit of frequency we see, because beyond that we will see solvent, diffuse layer dynamics, and those kind of thing. So usually our focus is more electrochemical cell aspect. So those very high time scales are not relevant or like important for understanding electrochemical cell also. So we usually work in millihertz to megahertz. So in that molar conductivity, this thing becomes constant at the.
Yeah, it becomes parameter.
Yeah, so that is why we don't go into that. But when you start thinking in terms of solvent dynamics, etc., those are very relevant. But just keeping focus for electrochemical problem, I am avoiding going in that direction. So in this kind of slide below, you can see the plot, which plots log of molar conductivity versus log of modified screening length. They show linear behavior in fit, and they have exponent, which for KCl it is 0.2, for NaCl is 0.47, for NaClO4 it is 0.63, and sodium nitrate it is 0.58. So as we said, like though it is acting like a sphere, a whole along with the cloud, but it is kind of soft sphere. So smaller is the exponent, softer is that sphere. So these exponent can be put into that equation, and one can do for arbitrary, not arbitrary, high concentration limit also. The last graph shows one is Onsager, the modified Onsager, which has a screening length in it, and can be extended up to say 1 mole. And our thing is start from above 1 mole or something. So the region which is more used by our all electrochemists for device and all those purposes. So let's come to popular thing for student purpose. We've done this kind of calculation. This is like lithium ion battery, very popular thing. And it was conceived by Witten Graham. And okay, so I'm blocking my view. Okay, so he conceived the idea of using intercalation electrode for this. So first version in it came in 1970, where he used titanium disulfide cathode and lithium aluminum anode. But it has suffered from safety problem, etc., but not for good for making a functional device. And then it was further modified by Budanov, and he recently died in June 23, and these and all of them got Nobel Prize for their work, and together jointly. And so he replaced this cathode with lithium cobalt oxide cathode in 1980, and this like lithium cobalt oxide act as a source of thing. And he also used anode as lithium aluminum thing, which again has some kind of safety issues or so, because lithium, if any leakage or etc. will have. Similarly, then further it was modified by Akira, and he used carbon, basically he used graphite to have anode in a lithium, and which replaces the lithium metal directly. And it was commercialized in 1991, and everybody knows it revolutionized our all portable electronics. Laptop would not be there. Your mobile phone will be have issue if you do not have this battery. Your drone, massive change in technology because of emergence of this battery system. So no wonder it was given Nobel Prize for has huge social impact and economical impact. And only after this, people are thinking of converting everything to battery-driven transport system, etc. So that like typical, what do you demand from these batteries? If you want portable electronic, you demand higher specific energy, higher energy density, high energy efficiency, and longer life cycle and longer calendar life. So this is okay slide from good enough talk only. And here we show the principle of this. Left side is my anode, which is my graphite. Right side is cathode, and which is kind of source of lithium here. So we have to charge our graphite electrode with this lithium ion, and then we discharge. That is what. And the amount of energy you can drive from like anode to cathode, the energy gap between that, you can obtain energy from here. So basically, in reality, and the kind of electrolyte you use is organic solvent, which does not react with lithium. And if you see that like factor which will decide when you want to commercialize, first thing is the cost, whether it's cheap or it's costly. And also availability of materials. That will also add to cost if materials are. So it involves politics, everything, because some country will have some material, other will not have. Then you have energy. It should have give high energy. It should give me high power, and give a good cycle life time for it, and should be safe so that it doesn't cause accident or deaths. And it should have least environmental effect. So all these parameter one has governs. That's why one do a lot of material research to find material which satisfy as much as possible these requirement. So the component which are enrolled in lithium-ion battery is lithium carbonate, dimethyl carbonate. These are solvent, propylene carbonate. You can see their size is like a fraction of nanometer. But how you decide this system? Because when you say interlayer graphite, distance between interlayer from center of carbon to carbon is 0.334 nanometer. But if you just exclude carbon portion, only the gap portion, that is 1.165. So lithium is smaller than this, so it can freely move inside these spaces. But sodium is larger than this. And all these solvents are larger than that. So obvious reason is that solvent should not enter into graphite, or only lithium should enter. So with this, you get the best efficiency out of it. So if you want to replace sodium, we will also show in calculation what will be the difficulties. These are just done to use physical chemistry concept, this portion of the talk, for the help of a student. Now, everybody knows Linus Pauling. You know Pauling electronegativity scale, you know work function, you know chemical hardness of ion, chemical hardness of electrode. All these things you know, you must have studied in your BSc. So how to use this concept to figure out when I put a lithium inside graphite, how much charge they will exchange or so, or how much. So this can be done if you know the work function of your, say, graphite or graphene layer there. And then you know the electronegativity of your lithium ion. Okay, if you are dealing with sodium, you have to know that also. And then hardness of this. So the fractional of charge of adsorption is the ratio of difference between work function of my electrode minus electronegativity, Pauling scale, and divided by the chemical hardness of this ion and electrode surface. And it is related to density, like chemical hardness of electrode is related to inversely to the density of electronic states there. So this formula indicate that only. And then here we have listed some of these properties. Your electron affinity for lithium ion is 5.39 electron volts. Similarly, you have ionization potential. Then because charge, so ionization potential is very high. Then you have electronegativities and hardness. So if you put all these things, find this fractional, and how much energy of adsorption will be there, you take the fractional charge which we obtained from here, which turn out to be for lithium is about 0.27 electronic charge, fraction of that. And for sodium, it will be 0.22. And sodium is also large, there will be barrier. So if I estimate this energy barrier, it is about 7.56 in unit of mean thermal energy at room temperature calculation. And now we want to see how to pack this lithium into my graphene interlayer. So, so here there is a concept of Zerum length or Bayram length actually. Bayram length is that when the Coulombic interaction energy become equal to thermal energy kBT. Okay, the distance at which two interacting ion or charges have that much of energy, that distance is called Bayram length. Okay, and this is basically dependent on dielectric of that medium. Here, dielectric of this medium is my dielectric of my graphene layer itself. And thermal energy. So if you put this number and the fraction of charge which is lost on lithium due to adsorption, that is delta A. So if you calculate for yeah, so when it is like Zerum length, they are not interacting because thermal energy it is available to it. So that will be my like a equilibrium value for that, how far these lithium can sit from each other. So it is, we have taken triangular lattice model to estimate that. And another we say, okay, now we want to see there is a adsorption energy. What will be length? Because I know this much is lowering for separation of these things. So you find that same Zerum length, you divide by if the factor that energy of adsorption is say scaled with respect to thermal energy is alpha, that's a number, then your this formula L lambda will get that. So we can ask what is the maximum packing it can do when your graphite is fully charged. So doing small this calculation, hypotenuse length and all those little trigonometric thing, you can figure out what is area which is covered under this hexagon or something. And then you say how many atoms, because these hexagons are repeating. So only 3 lithium ion per hexagon will be there. So you figure out the density of this thing per unit area. And then you say the separation between your graphite interlayer, which will give you volumetric density. And then people who work in this area, they go into kg, etc. You multiply with the density of that. And if you scale because Ni is the density, and then is electronic charge, V is like my nominal potential, which is 3.2, 3.6 for the lithium ion battery. And you divide this, you get a number which will give you energy density also. So this is a very simple calculation, and it's a back of the envelope type of calculation. I've just calculated for the help of a student who will be listening that, though battery is a very complex thing, but we can estimate a few things in battery. So here those numbers are dated. If I do calculation for lithium, and on x-axis, if you see, I have plotted Bayram length divided by intercalated ion distance. When battery is fully charged, this number is large. And when battery is in equilibrium state, we can say this number is 1 or so. Like it is discharged, so some ions are still left because they're no more interacting with each other, they are there. So in the case of lithium, we find the fraction of charge we have already discussed, and packing length of ion, the maximum packing length, you can, when you pack maximum lithium ion, it is less than a nanometer, 0.95. And when you have like Bayram length, which is of 7.6 nanometers, so well separated, like when it is discharge state. So with this, you can calculate that equation for energy density, which it's more scaling results. You get 6.42 watt hour per kg. I'm using this unit because this is typical battery, people use this unit. And this is a typical value you get for lithium ion thing. And usually in battery people, I have just scaled with respect to weight of my or volume of my graphite electrode. They scale it with respect to whole battery weight itself. So my number is 642 and their number is 120 to 260 watt per kg. This is literature values are given below. Similarly, sodium shows much. First thing, you can put less number of ion in a fully charged state for sodium, same case. And the overall energy density is also lower for it. That's why sodium is a struggle to put into same thing. So people are working over. And if you want to find power density, these are two things usually all these people talk about that. And that is power density, because what is deintercalation time will decide the power density. So deintercalation time, if it is tau h, a typical some fraction of energy will come out in that time, or some 50% or so, you will get the maximum power you can achieve from this battery. So with this, I kind of put closure and come to more realistic thing, which I do more. And this is dealing with the how to, what is electrochemistry? You just play with the energy scales of electrode. Because all this modifying electrode is nothing, but you are trying to play energy scale so that it becomes favorable for your electron transfer or storage of ions in it also. That's only goal. Or it favorable, so that favorable electron transfer you can use as a kind of sensors or whatever way you can increase the rate and see the detect your thing, species which are not. So people do modify this thing in a various way. You can put a kind of, in natural, if you take a metal, you always have atomic steps. So if you increase atomic step density, you can alter the energy both locally as well as in an average sense. Or you can absorb some ions, maybe some halide ion. They also alter. People do use that. Like chloride adsorption is responsible for enhanced corrosion. That's why groundwater is not suggested to make your lantern or so. And then you have another thing is like you can put cluster of atom or atom over it, like over the adsorbed state. That will also alter your local energy scale. So you will have fluctuating energy scale over it. You can put graphene and any other two-dimensional material. You can make alloys. You can make conducting polymer. This is what all people do. And you can deposit nanoparticle or nanodots, as in the morning lecture. Or you can intercalate, you can make porous. Well, there are various ways to alter this energy. The game of electrochemistry is to alter this surface energy so that it does efficiently electron transfer or accumulation of charge in that interface. So if you want to make supercapacitor. So where this energy is reflected in an electrochemical measurement, observable, where you can see these changes, is one is called potential of zero charge. When we do electrochemistry, if you make capacitance plot on x-axis, you put potential, and in that plot you get a minima. That minima point of potential is called potential of zero energy. And this potential zero energy is also responsible for electron transfer kinetics, barrier in electron transfer, and it's also responsible for formation of electric double in electrochemistry. So it has components. So both are like, we call it tailoring electrochemical work function, because this work function has adsorbed layer of ion. It has dipole of solvent. It has metal, irregularities on metal, everything accounted. So if I see component of this, it has work function, first phi E naught. Then the electronic reorganization energy due to presence of any solvent or adsorbate. And then you have a orientational effect from dipolar solvent. And then you have, okay, if it is chemi-adsorbed species. So if you want to relate this work function, which is with respect to vacuum reference, and when we come to potential of zero charge, usually we have either NHE or calomel electrode something. There is a constant which has to be subtracted out to map into that. So this is observable, and this we exploit in formulating our electron transfer theory extensively. And then there are kind of many phenomena can happen, as we discussed in first or second slide. There are many things can happen. There is an electric double layer always present, which modifies whatever we do. So if I do pure material calculation for my electrode, DFT calculation, etc., if I don't bring into interaction of solvent and other thing at interface, it will not predict it correctly, and it will not be much useful for electrochemical analysis or understanding, because it alters, because electrochemistry sees interface, not the bulk of the material. Okay. Then you have kind of have phenomena like adsorption, intercalation, which can alter your properties. Then you have charge transfer on electron transfer, etc. And then you have another transport like diffusion, migration, and ohmic also always intervene in electrochemistry, because the potential which will reach at my, say, activated complex or in the my electrochemical cell will be always moderated by this ohmic loss, V is equal to IR. So more current and whatever ohmic loss is there. So the what you are applying intended to apply for enhance your kinetics will not reach there. So that way you have to carefully account your ohmic also. And you can have coupling with bulk reaction synthesis. I will do a lot of ohmic synthesis. And all these phenomena has their own characteristic time scale. They have their own length scale. They have their energy scales. So if we understand those scales, it will be it is easier to formulate theory like, say, scaling theories without even going into too much detail and getting stuck with a difficult mathematics or a computation technique. So the first thing we will focus in electron transfer theory. So everybody knows Marcus' work of electron transfer. Biman Bagchi has worked also on this area extensively. And here, Marcus have kind of basically thing differ from other usually is he has reaction coordinate also free energy, and the rate of reaction depends upon this reaction coordinate, which involve largely the solvation energy and other part of the system related information. So when it was homogeneous system, both species have similar effect from the solvent reorganization. But when you replace one species with electrode is a large system. So it can have all possible configuration or states coexisting simultaneously on electrode. So that's why some of the Marcus approach where he ignored the electrode aspect, though he has potential here in this thing. So the rate constant here is basically prefactor, which is like a frequency factor, or in electrochemistry, there is a length also scale, which gives centimeter per second dimension. And then you have activation energy scale with respect to thermal energy. But the formulation of activation energy in Marcus theory is everything is scaled with respect to solvent reorganization energy, including electrode potential, or it also account bringing in work, reduce species to the surface or taking it away to oxidize species, or like that. So, and then also there is a transfer or coefficient for potential. He used more kind of a phenomenological way of doing electrochemistry, where you take derivative of with respect to potential to get that. So these are all have issues. Why they have issue? They have issue because you have this major defects arising from, because there are two states in electron transfer at heterogeneous interface. First, your electroactive species has to reach up to OHP. Okay, that is so kinetics of electroactive species or electroactive ion arrival at OHP is important. And it will be seen when electron transfer become very fast, then only the ion arrival kinetics control it. That we will call barrierless electron transfer. But it will have some finite rate, not very so it limited, but finite. And then they have metal dipole interface. The modified version of even Marcus theory, they use bare metal density of state, but when we put solvent over the metal, it changes all distribution of this density of state. So that averaging will not solve the problem. Then it has frontier molecular orbiter and energy fluctuation due to solvent. It is accounted in Marcus theory through reorganization energy, but problem is that electrode is a large system, so it does not follow exactly the thing which is you do for electroactive species. Then there are kind of crystallographic disorder, etc. King's staffs, those are difficult to account because electrode is missing more explicitly in that theory. And there's a question how much potential is transferred to the transition state, because electrochemistry, you can alter rate of reaction by changing the potential, and potential can be varied, like as you can vary, you turn the knob and speed up your fan. So that way you have freedom. That is why electrochemistry becomes very convenient topic or rich to do a lot of things which you cannot do in homogeneous reaction thing. So, but in their theory, they use it more phenomenological way, not independent model for that. So we have kind of avoided all those things while doing and made it more amenable for more complex electrode, which I showed in an earlier slide. So basically in our theory, we say alignment of Fermi energy level with FMO of electroactive molecule or ion is responsible for electron transfer. So it has two components, our activation energy formulation. One is electrochemical work function, which is directly measurable in electrochemistry as potential of zero charge. And there is a fractional charge of activation because FMO and my metal, their energy level are separated. To make them transfer electron, they have to become equal. So this is a kind of delta dagger represent the fraction of charge required either to inject or eject out of my, say, metal Fermi level to make them equal or something. So that way, these are the two components. The whole thing is how to model these two things microscopically so that we can have all microscopic components, both electrolyte, supporting electrolyte, the size of ions, type of metal, and any solvent, formation of adsorption over interface. All those complexity has to be accounted. So idea is simple. First calculation, let us ignore the part of my solvation reorganization energy, which we add later on as correction in our model. Okay. And so like my Fermi energy level is interacting with, say, LUMO orbital. If I say work function penalty required to take out some electron to match my Fermi level with the LUMO, and if I say that I need some delta dagger fraction to do that, and I add that to it, so my energy level will drop. Therefore, my effective work function will increase. So on left-hand side, you see that, okay? And similarly, if I do it for HOMO, which is higher than this, I have to subtract, I have to inject some electron to it. So the work function, the level, Fermi level goes up, work function decreases. So this, it's a simple calculation. And since there is a negative sign in LUMO HOMO, so I put minus in front of it to equate it. So, and finally, if you rearrange, unknown delta dagger can be determined in terms of work function of the electrode, LUMO HOMO energy of the work, electroactive species, and Fermi level of that. And then we do correct. I'm not going how we do it. Okay, cumulant expansion method we use and those things. But the final thing, the first function get modified with the second thing, where sigma f represent the RMS energy fluctuation in my frontier molecular orbital. Also in Marcus theory, you do not have very explicit representation of frontier molecular orbital, though most of the kinetics we think it should depend upon only for frontier molecule. So in this thing, my fluctuation, the RMS energy fluctuations to lambda as KBT. So it is dependent on both reorganization, more reorganization energy, more fluctuation, and more facile will be electron transfer, and the thermal energy. Okay, so the effective, like if I compare with my, with ignoring my fractional charge, solvent reorganization component, if I include it, subtracts out of my that value where it was not included. And this delta F dagger is represented through in terms of ratio of my work function of my adsorbed state, okay? And the Fermi energy level, say scale, it is scaling, and the solvent reorganization is also scaling with respect to Fermi energy. And typical variation of this solvent reorganization energy is 0.4 electron volt to 1.2 electron volt. So effectively, we picturing it is a Gaussian distribution of my FMO orbital energies also. So effectively, we get a kind of reduced activation barrier because my fraction of fractional charge required to match that energy is reducing. So like solvent reorganization act as a facilitator in electron transfer kinetics. So, okay, so let's see what is this fractional electron transfer. I have plotted this here. This is done keeping some data also in mind of Terasati, which ferrospheric system, and another system, a ruthenium hexamine type of system. And here delta dagger. So the sign indicate one is work function is rather larger than my magnitude of my this FMO or smaller. So on x-axis we have plotted the difference of work function and FMO energy. So it can have both positive, negative sign. There's zero. So for certain type of thing where LUMO, which is our ferrospheric system, active orbital with LUMO energy, we plot, and the fractional energies come, except this gold stand outside that thing. And then we have data, other data where also it has. So here we learn smaller is my fractional activation charge. Faster will be reaction. On the middle portion where it is close to zero is basically barrierless electron transfer on electrochemical system. As it goes further away from that value, larger is this fractional charge. You will get quasi-reversible or even irreversible if this becomes larger. So here is the plot of this my fractional activation charge and activation energy. So there is a central region where fractional activation charge is near zero. These are the region where kinetics is barrierless, if you can see here. And similarly, as the activation energy increases, becomes reversible or Nernstian charge transfer in electrochemistry context. And it is like up to say 8 kBt energy, it is barrierless up to 8 or 10. Okay. Then you have up to say 15, 16, you have reversible charge transfer. Above that, you have quasi-reversible charge transfer. And this lambda is as we increase the solvent reorganization energy, this activation energy decreases for 3 different reorganization. And these are kind of various parameters. To plot this, because we have made continuum plot, we have assumed that Fermi energy is approximately equal to 1.8 of work function of that. This we averaged over various Fermi energy. Okay, it's not true for graphene. For good metals, this formula is a good approximation to plot. Okay, and then reorganization energy and Thomas Fermi length and size of the metal, dipole of water, HOMO and LUMO energy. So these are the input parameter you require to run this theory, get the quantitative values from this theory. So here I am plotting log of standard rate constant, which has dimension centimeter per second, electrochemical rate constant. And then you have a fractional charge. So when we plot with respect to this, so we have like a maxima, like in Marcus also you have some kind of maximum there. When you playing with the reorganization energy, here it is the difference of work function and my FMO energy, which will include reorganization. So in the middle where this fractional charge is small, you have a barrierless electron transfer. This is the highest value, more than 10 raised to power 200 centimeter per second or so. And as this fractional charge of activation increases, whether injection or ejection, it will start decreasing the standard rate constant. And lambda as if you increase, it will increase my rate constant. So this is the conclusion from this theory. So in the central portion, you have barrierless electron transfer because here it is controlled by ion transfer kinetics. And this is like with data, same plot. We have accounted solvent rearranged. We have accounted even because it's the solid metal, so atomic step corrugation. This data did not provide us that. So we have put some average level of that atomic step in all calculation. And here data of Avesta and another is Saraswati, where various metals are plotted over it. And this is my theoretical curve. And it is plotted continuum. The metal will have a specific work function and Fermi energy. And that is circumvented by using this kind of approximation by averaging over various ratio of work function over Fermi energy, which is about 1.8 factor for good. And there's kind of calculated numbers and how it matches, except this gold where deviation is large doesn't satisfy. Other satisfy theory much coherently. Another question is like how to bring in now atomic step, because we promised we can bring in through our theoretical methodology complexity of electrode, more realistic electrode, which I use for devices and all those things. So first attempt for explaining is first is more simpler case of atomic steps. Like your electrode is homogeneous, but energy heterogeneity is happening because of fluctuations or curvature changes at the atomic edges or so. And this is very important for both electrical double layer electron transfer, catalytic activity, adsorption, and a lot more things. So here we model our like a step as a like 10 hyperbolic function with a fluctuating as this xi tilde of y or something. So this is where we model it. And then there is a kind of periodicity in it because hyperbolic function. You can repeat things. And then there is a height of my step is hs. And A is my lattice parameter. And this is my edge fluctuation in that. So definitely we have taken it random. So we have to do certain averages before theory becomes functional or something. We did all those things to account that. So number of step, which is a one important parameter for when you have a step, it is inversely related to average tiles width. And people do experiment by measuring this quantity and reporting the electron transfer kinetic. And the functional range of these atomic steps, where atomic steps start influencing electron transfer kinetic, is 0.1 step per nanometer to 3 nanometer. Beyond that, you cannot pack because then the terrace width is smaller than atom or something. So that's the upper limit. And we obtained formula which did not exist earlier, like even density of kinetics per unit length, which is the fluctuation at the edge, mean square fluctuation. This is h square. A is my lattice parameter. This and lattice parameter, it gives me kink per unit. And this we obtained by putting our theory for work function to the data which is available for step density dependent work function for various metals. And we could figure from fitting our data, we could figure out NK through our equations or something, which is not available in literature. And then finally, I'm jumping a lot of things and coming to that like an experimental thing. We are experimentalists by few group, and they created various cut angle and got metal surface which varied the step density per nanometer. And they showed the oxygen reduction process, ORR, on single crystal platinum electrode with various cut angles or something. And this is a kind of red is our theoretical line. And these stars represent their point or something. So something strange is happening in this area, or maybe if they repeat this experiment with their error bars, maybe it is within error also. So here we have kind of accounted solvation steps. So various averages are done over randomness in steps, randomness in fluctuation in solvent related energy, FMO, and all those things. And so if we totally represent the complexity which occur in electrochemical or heterogeneous electron transfer, we have kind of spatial scales or spatial related issues, and then we have energy scale. So spatial, we can have this material surface, which is about 2 atomic distance or spillover electron plus 1 atomic layer of atom, up to which it influences the thing. Other is bulk. And here you have a metal, you can have nanoparticle over it, which will complicate it, step skins over it, which will complicate, put 2-dimensional material, make alloys, all these possibility you can. How we account in our model, we use gallium approach with our own approximation. We are not using a standard gallium approach, but physical idea is same. And then we find what is curved gallium work function or electronic capacity. Work function, electronic capacitance related to each other. With that, we can kind of play around with geometry and lot of things, or to atomic step level. And then we have another thing is first layer of say solvent dipoles at the interface. This is very important to include because most of the people who are doing computational extensive, they avoid putting this solvent because electrode will see through this solvent layer. So you have dipole layer. If you have pH also, that will also have some kind of HIN or OHIN adsorption at the surface, which will change the property. You can have chemi-adsorption, which will change, and you have electric field, which will interact with all this dipole, which is emerging out of metal, which is strong, but is very short. So we need for that concept of say electrochemical work function and potential and capacitance of zero charge, which has all this information and experimentally measurable and theoretically and modeling it. Then after that next layer, these are all dynamic layer is OHP, but classification like this helps electrochemists to convey the message. Electroactive molecules, ion crossing double layer and OHP, ISP out. So OHP is the kind of solvated ion which can closest approach of solvated ion to the electrode surface. Okay, that is called OHP. And here you, if you have electroactive species, you have to know homolumo level of that, that goes into theory, and contribution from solvent reorganization to this thing because they are possessing still their solvent. And then partial charge of activation required to match the energy level of electroactive and metal surface or with my electrode interface. And transfer coefficient of potential, because the potential which is operative is what is potential existing at the transition state only. So where is your transition state? You have to know where is your transition state, or you have to estimate location of your transition state to get the correct transfer coefficient. And we have modeled that also by solving equation at certain approximation level, but results are very neat, clean. And then you have diffuse electric double layer at the end of it. So anything transfer across the, goes up to the metal, it has to pass through the diffuse electric double layer. So it can be repulsive, it can be attractive for approaching ion or so, but it is always dominantly repulsive because when you are bringing a ion from the bulk to the 2-dimensional surface, so you are reducing its 3-dimensional freedom to 2-dimensional. So there is an entropy barrier, which has to be accounted. Some of our calculations are based on estimating entropy barrier of transfer of ion from say bulk to the surface. That way also we estimate our that ion transfer kinetic barrier also in earlier discussion. So here you will know because dielectric at the metal surface is slightly different from at dielectric at inner Helmholtz plane, dielectric at outer Helmholtz plane, and diffuse layer and bulk dielectric. So one has to account that. So we do solve this.
Ramakant, it's about time to close. It's 5:30.
Okay, I will converge now. Okay, so these are all complexity can be accounted through modeling or something. So we use this model to solve problem, both like king to step. Also, we kind of solve problem where how nanoparticle, metal nanoparticle interact SARS-CoV to spike protein and denaturation kinetic of that on metal. And use because approach is generic approach for molecular devices also, which I'm not discussing here. Then I think I will now converge down, double layer. We have this structure. Then we kind of think there are two simple equations. Any equation on Earth, if it has 3 parameters, it's the simplest. E is equal to mc square. These two equations, H is equal to root of d by omega m. So when we do experiment, we get a maxima in our phase. If I do electrochemical impedance spectroscopic experiment, where my reaction is fast charge transfer or diffusion control, you will get a maxima in your phase angle. The frequency of that maxima and diffusion coefficient of your electroactive species then is related to RMS height of my rough electrode. It's kind of giving you very simple handle to measure in situ roughness of electrode. This is not a traditional electrochemistry, but if you keep think both backward, forward, you can find such relation. Another quantity which also always important for electrochemistry, what is my electroactive area? How much it is there? Because we are making very complicated electrode. So geometric area is not the real electroactive area. So when you do kind of impedance measurement, there is a crossover inflection point. That inflection point frequency, one is idealized case of say omega h naught, and one is omega h, any rough electrode or something like that. And the ratio of that frequency gives you ratio of their capacitance, which is actual electroactive, how much double layer is there. That number is your roughness factor, like microscopic area over macroscopic, which is electroactive available, which is any gas type of measurement will not give you that. So there are kind of argument how we do that. Some site will pack more of species, some will less. So since time is ending, I'm kind of running down. You use some of this beautiful formula of Steiner for how, because when we have electrode metal surface, if I put a say OHP or a solvated ion, it will be slight distance away from the metal. So the two parallel curved surfaces, how the area will change, that Steiner formula help us to get those number. And it also kind of the size of ion and the local curvature of that also. And it's so measurable, and it can give you kind of a ratio of capacitance in term of, and it can provide you also what is my overall surface mean curvature also, like in unit of my adsorbing ions. So I'm just rushing up. Like this is like kind of we do experiment as Ranjit mentioned. We made some set of rough platinum electrode with different roughness factor. You can see in this third column, starting from 4.5 to 124 roughness factor. Like microscopic area is this time larger than the macroscopic. If I take a wire slender area, so your macroscopic geometry you are dividing. And then you get kind of what is my active, like the roughness factor, which we obtained from this equation. It is listed here, then this, what is mean curvature out of it. And then this omega h you can measure as well as omega m. One is from diffusion thing, RMS roughness, one is about roughness factor. So you can measure it them by a separate, one is EIS, which we are giving you in green column. Then another method we made long back, CV-SEM method, where we utilize, reconstruct SEM image using a area determined using CV. Okay, some denoising and all those things we do. And the AFM measurement. AFM measurements are like envelope surface, so its area will be always less than the actual area. So that you can see it is here always. The thing which you are obtained electrochemically is larger than which you obtain by RMS roughness. So FM is not accurate method to find area of your electrode. So finally, we started with this slide. We have materials. There is a game to play with materials. But in electrochemistry, you will not be seeing material, you will be seeing phenomena. And phenomena only control your electrochemical device. And phenomena is controlled by spatial scale, temporal scale, and energy scale of that phenomenon. With this, I will thank you all for your patience. All these students, they've contributed. Some has gone to industry to model batteries for transport sector in Europe or something. And other are pursuing either teaching or some academic job. With this, I thank you all. If any question for me, I can reply.
Thank you, Professor Ramakant. Shuman.
Thanks, Professor Ramakant. So because of shortage of time, maybe we'll take just one question. So I think Professor Praveen Ingole has a question. Praveen, if you are around, you can ask the question directly.
Yeah, thanks, Professor Ramakant.
Oh,
The question is related to the PHC. You mentioned the chemisorption term is also included there.
yeah.
How do we experimentally get an idea about this extent of chemisorption using the PHC?
Yeah, it will shift your PHC if you kind of say change concentration of chloride in your solution, and you see the difference in without chloride, say PHC. The shift amount is directly related to the extent of adsorption of chloride and your IHP, because it has to see that PHC sees things which are at IHP, because OHP is absent at PHC, diffuse layer is absent. You have some contribution from bulk capacitance because the bilayer is forming everywhere in the solution for each ion.
So you mean you have to change the concentration or the ionic strength, and then you
it's a
look
shift
at the
in, shift
shift
in
in the
your
PHC.
one way to characterize. Whenever you see shift in your PHC with change of your electrode condition or electrolyte condition, that change correspond to your chemiadsorption or something. Okay, if your electrode is fixed, if you change electrode, it will change PHC.
Certainly.
Solvent.
Thank you.
Thank you. Yeah, there are some other questions in the chat box, I think, from Mr. Ravi Kishore. So I'll send those comments to you by email. And if there are some other questions also, we can share maybe by email directly to Professor Ramakant. So once again, I thank Professor Ramakant and also
Anshu Pandey
for the excellent lectures. And on behalf of all the organizers, myself, Professor Ranjit Biswas and Rajiv Biswas, I thank all of you for being here till late afternoon. And so thanks once again. And we'll announce our next seminar very soon in our mailing list. And both of the lectures today have been recorded, and they will be made available on our YouTube channel for those who have missed today. So yeah, thanks everybody, and yeah, see you soon. Yeah.
Thank you.
Thank you, everybody.
Bye. Bye, everybody.
Bye-bye. Bye-bye.